Hello everyone. Today I would like to show you how to use S-parameter and S-parameter files that you can get from RF measurement equipment or sometimes from manufacturers of RF devices, and use those files in your AWR projects in order to simulate and basically design an impedance matching networks. So let's start with new schematics. I will show you example of loop antenna. This is a delta loop antenna that I've measured using the light VNA 64. It's basically a device very similar to NanoVNA. It uses almost identical software, and saving the S parameters to S1P file, which includes only the data for one port, looks like this. If you are not familiar with this file format, this is an industry standard, also known as a touchstone file. Here Keysight has a useful examples and shows you how this file is defined. So you have comments, and then of course you have to have this row that shows you the stimulus and the real, the imaginary part into also what resistance of a port. Now there is some discussion, let's say in the industry, about NanoVNA and some version of the firmware, because from what I've gathered, for example, the Keysight test bench, for example, might complain with this file. And if you want to see a real Keysight file, it looks like this. The only difference with more columns is because I've also measured this two-port. This comes from a real two-port vector network analyzer, this E5063A. And as you can see, of course, we also then get the transmission from the second port to the first, the reflection on the second port. So you have both, for example, the isolation and transmission through. This is actually a bidirectional device, so it doesn't matter, but you can see a little bit more information, including the fact that the calibration was performed on this port. I'm not sure why NanoVNA firmware doesn't give you these parameters. This is really not that much, but this is a tangential thought that just, might be useful to some of you. So let's start with capturing the schematics. So we need basically a block for the S parameters, and there are a few that you can use. I will use this N port F, which basically allows me to load the S parameters from a file and define the number of ports. But if you are using with two-port devices, you can use the 2 or 4-port device, and you can also define this parameters yourself. So let's go for the N port F, and if we go to the properties, the first thing that I do is I will define only one port. It will change also the symbol of the device that you will see in a while, and I will load this loop S11. Okay, so let's see that it did change. Okay, I will add the port. This is a 50 ohm port, and connect it one to the another. Now this doesn't look really attractive and doesn't tell us much what this block is. It's just a black box, which is kind of the idea of scattering matrix and S parameters if you think about it. But under the symbol tab, you can change the looks of your symbol. So if you are working, for example, with filters or like transistors, you can choose whatever stuff suits you, but this is an antenna, and in fact we do have a symbol for a antenna, so I will pick this. Okay, and now I will prepare a new graph on which we will plot the S11 parameters. The Smith chart would be also a very good example, but I think it's just already simple, and I care only about the reflection for this time. So let's call this this rectangular S11. Okay, let's create this plot and add two measurements to it. So I want to use DDB, and again I care about S11. Okay, so now remember that we also need to define some properties in our project options. So I've started my S11 file at 0.00115, 1.5 megahertz, and it continues up to 15 megahertz. So this will be 15 megahertz, and I will go with point, I think I did have 1001 points in this file, so something to approximate this should be somewhere around this range, right? Yeah, okay, maybe a little bit more. Yeah, it will work. Okay, so now let's hit on a simulate or analyze, I guess, and you can see we do have a perfectly low reflection around 7.156 megahertz, which is an amateur radio 40 meters band. It's a very low frequency, of course, for which the microwave office is usually used when compared to what we deal here. But just remember that, you know, higher frequency will be just, you will put 2 or 3 more zeros here, and all other actions will be the same for you. Okay, so this is our real measurement, and we can compare this with a software called NanoVNA Saver. This is a very nice software. I use it all the time on a Linux. On Windows, sometimes it's not very stable, but it's an open source project which I will link in the descriptions. As again, I've mentioned, it works on both systems, and it works relatively well. We have here indeed this minimum. I think it even tells us that this minimum is 1.56. So this is exactly what we have seen in AWR Designer. If you don't believe it, you can always use the auto marker with option for a minimum and just put it here. So exactly the same thing. Okay, so now what I want to do, because no, yeah, this is cool, but I want to match this antenna so that I can use it on the lower bands, which will be around 3.65 megahertz, so almost half of that. So I will put the marker at 3.65 megahertz, and you could read this also on a Smith chart from MWR, but this is something that everyone can use. It's an open source tool, so I would always encourage this. You can read the parallel resistance and parallel capacitance of this, or I guess reactance. What is nice is that if you buy, for example, crystal filters, they will often also give you this value. So this is like 1800 ohms and 5 picofarads in parallel circuit to determine the impedance of the ports. And another example from college, they also give you the termination impedance in this complex form. So we will read those values. Sorry, here. We will read that we have 4.37 kilo ohms and 26 picofarads. And we will use this impedance calculator by analog devices. Later on, I will show you how to use this, how to do this directly in microwave office, but this first will be just a validation of our as parameters and how just to show you how to use them, and then we'll do something more advanced and appropriate with the software. So I will choose parallel complex load. You can also define this in terms of your magnitude and phase that can be a part of the S parameters, but we will go for this parallel load. So let's put 4373, so this will be 4.373 kilo ohms with good enough precision for us, and 26.017 picofarads, more than enough, I would say. Now, because this is very frequency dependent, we will also need to change this to 3.65 megahertz. And everything is fine here. You can see that we are given this value, of course, in positive picofarads because of where the point of the Smith chart will land. And as you can see, it's very close actually to this crossing point. And because this resistance value is very high, we are almost at the open side of this Smith chart. And our goal will be to broad this point using the LC components right here, right to the middle, which if you look at the minimum is basically where the 7.156 megahertz is. This is our harmonic. You can see it's quite close, but maybe not so much. it's around 2 to 1 SWR. Actually, it's better. It's 1.5. Here will be well, like 2 to 0, right? Okay. So in these analog devices, we have calculated the values in microhenry. So this is quite high inductance and picofarads. So what we can do, just remember that the microwave office has this global definitions of units. I will change this to picofarads because this is a ridiculous unit for RF work. I mean the microfarads. We don't use them usually in RF, and everything else seems to be okay for me. So I will just put okay and go back to the schematics. I will copy this because the definition of the S parameters and the port is okay. And the only thing, maybe I will need a little bit more space. Okay. So I will use the lumped elements of inductor in series, and also I will need a capacitor. So this is also a closed form. Press right mouse button to rotate it. Also, of course, add ground and connect everything to each other. Now, what you might be asking me right now is that why we have this suggestions of two circuits, and the reason for that is that this will have a low pass characteristics, and this is just a equivalent circuit with replaced components, and this will have a high pass characteristics. Later on, I will show you more complex structures that combine low pass and high pass circuits to create a higher bandwidth of this matching. But here we care about something simple and quick. So right, we should probably actually set not nanohenries, which is what I usually use in higher frequencies, so sorry for that. We will actually use this feature to set microhenries, because why not? We are dealing with relatively large inductors, and as you can see, everything was translated, so that's actually neat. 20.27, 22.72, sorry, no, 27. Yeah, 27, sorry for that, it was, the ending was 72. 27, we don't need more, and I think it was 66.78, right? 66.7, okay, 66.7 pico. All right, so I will save as a delta loop, maybe, because that's the type of antenna that I've measured physically. And let's add another measurement from this P indicates the port, so this will be the port 222, and add the measurement of this reflection, and on this we'll hit simulate. Okay, this is abstracting our view, and as you can see, this pink trace is for our matched circuit, hopefully to the right frequency. So I should probably also use the auto marker, why not, and look for a minimum right there, exactly in the place that we wanted to, and the impedance matching here is excellent. It might be not very narrow, but if we assume that you want this at least minus 10 dB, it actually shows 3.559 to 0.75, so that is relatively wide. In reality, of course, this inductor will not be perfect, it will have limited Q, so the bandwidth will also be probably not that sharp and not that good, but you will have to define some other parasitic components around this inductor. This is only to show you the S parameters, how they work in practical examples. So let's put also another circuit, and this will be more complicated, so I will make more room over there, and I will actually delete these lumped elements for now. Let's go to the wizards, and we'll use something that I've shown you before, the filter synthesis tool, but instead of design and synthesis, we'll go for matching. And here you can define the source in terms of either, again, complex impedance, or here you have your parallel and parallel or resistives and so on. So you can go through this and see what kind of terminations this software expects from you. But we will choose this 50 ohm port because that's what we have ideally. And in case of data, the software allows us to load the S parameters. So I will go to my desktop, and here you have to select that I want to measure the S1 parameters. Okay, so this is only for one port, and the automatic frequency range, this should be fine. Let's go further. And this, in this tool, you can see that this looks very familiar to the filter synthesis tool. You can choose either to use the end sections of this pi configuration. So if I want maybe broader match, I can play around with this, right? So this is what you can expect. So this actually doesn't work here that great, but we can go for something that I know will work relatively okay, which is this L, P, and T configuration. So this looks like a T, of course. If you have something like this, it looks like an L, and P is, of course, this configuration. So here's is what I've mentioned to you is that you will have both high pass and low pass configuration. Uh, in the window before, I could have selected a wider frequency spectrum analysis, so I would see here how this low pass characteristics looks like, but you can see that it's combined together into some sort of a bandpass filter, almost like. Um, Again, you can go for 3 sections. So this is the pi configuration here that you can see, and it's a basically combination here of this low pass filters and so on. So very nice. It also adds sort of a pre-selector to your antenna. And if you are familiar with tube amplifiers, they've used circuits like this, for example, to match the impedance of the final stage of the amplifier to the antenna, and also provided this low pass characteristics. So let's go with maybe something that will be noticeably larger. So this T section looks quite interesting. So let's go for it. Also, don't forget to put here the frequency, the design frequency, because the AWR will try to match something for you depending on what you put. And you can also define the Q of the circuit. Now, I will not play with it for now. This is only to demonstrate that how this works in action. And you can also look at the lists. Here we've got the warning because this is we are dealing with really high impedance in this case, right? This is like a few kilo ohms or something. So let's go further. Again, you can look with different spans and so on at this network. So this is actually quite handy. I wouldn't expect the circuit to be this wide with real Q of such a high inductors, because this will have some resistance. You can actually change and play with this here, but I will just skip it and go further. Of course, I should probably first save in some way those values. Um, so we could, of course, generate the design with this option here, but I want to put this on the same schematics as before. Good thing that it actually saves. So I can use now this values in my schematics. So let's recreate this just quickly. Okay, so we are ready to test this third option, which is matched using a little bit broader network generated by AWR. And as you can see, this brown line is maybe not super visible, so I will go quickly to the options and traces, change it maybe like to a red. That should probably stand out a little bit more. Not really, but let's make it. Oh, okay, this is good. So yeah, I guess you can see that it has also the same minimum, so I will not bother to plot it, but it has this nice elbow which broadens our span a little bit. Just as a short reminder, let's take, for example, this, let's rename this to CLT for the L circuit of the capacitance of L circuit and tunable. And let's press Ctrl E and CLT over here. The value here was, if I remember correctly, like 66.7 picofarads. Actually, I've changed the ID, so this should be like C1, and here we need CL and T. Okay, sorry, a little bit small screen on this laptop, so it's sometimes more problematic. And now, of course, we can use the tuner tool, which is a very handy part of this software. Again, simulate this once more. Yeah, it works. And now moving this tuner, we can actually retune our circuit. So you can see that, for example, at this frequency, we can achieve better reflection, and of course, increasing the capacitance lowers our resonant point. So if you design, for example, automatic antenna tuner or just tuning circuit for your network that has a switchable, for example, capacitor or variable capacitor, you can very quickly verify whether the capacitors and inductor combination that you used will span the entire band, for example, and you can measure these points, and then knowing those values, you can put them, for example, into a lookup table of your automatic tuner, and you will have a matched antenna, at least in theory, but it's a good starting point. That's where I'm trying to get to. Now let's move to maybe a little bit more advanced example that how these S parameters can be used. Okay, so here is a more complicated design of a UHF amplifier that was enabled thanks to this S parameter simulation in AWR. So basically, it uses the BFR92 transistor as a discrete amplifying components, and I've put more on my web page if you are curious about this tuned amplifier. I've described how you can design something like this, so I will not go into the details, but what you should know is that the S parameters and the reflection on the ports of this base and collector, they change with the collector emitter current and the current that flows through collector to emitter. So the manufacturer in this case on semi, sorry, the Infineon, in this case in Infineon, delivers us not only the models for Keysight ADS and Microwave Office by Cadence, but they also deliver you a SPICE models, which is of course more simple model than those two nonlinears designs. They also deliver you S parameters in zip. And if you unzip this, you will have a lot of S parameters measured for different collector emitter voltages and different collector currents. So if you perform the SPICE simulation, then you will know those two values. You can choose appropriate S parameter file. And around this, using the filter synthesis tool, you can, of course, design your matching network. I guess you can see I have tried this a lot of times for input and output. And one problem that you might face is that, here you can see this definition, what problem you might face is that designing one network will load this, of course, structure and change slightly the impedance at this port depending on the isolation of the device. So if you have like microwave integrated circuit MMIC or something, that the isolation of this will also depend how this network loads other port. And another thing that is important to remember, this is an acceptable method for a low signal amplifiers like this LNA that I've designed. If you were designing a power amplifier, for example, this might be more complicated because you would have to use a load pull method since high power devices will experience more nonlinear effects, and nonlinear methods of load pull are necessary. Load pull is also available in Microwave Office, but it's not part of this tutorial so far. So why would you want to even design something like this if you can go to Mouser, for example, and buy like already pre-matched MMIC that will have higher gain and maybe it will be much more broadband, and it's because if you are using this method, you can match exactly where your impedance will be, and because this is a tuned amplifier, it might help you with elimination of some of the harmonics, for example. So you can see that this amplifier will actually work quite poorly for the harmonics of this 433 megahertz signal. So for example, for amplification of intermediate frequency, or for example local oscillator that is constant in frequency, this is actually a pretty nice choice. Of course, it requires you a lot of time to design this, but um, as an engineer, you have a freedom of choosing the gain, the noise, and the bandwidth of your amplifier, instead of relying on a ready solution that will not be possible to accommodate maybe to all those parameters. Also, very interesting thing is that the peak of the gain, the maximum stable gain, is not the same as the minimum return loss. So this is one compromise that you have to make, for example, and the noise will be, of course, the third compromise there. But this will probably come in the future tutorials. This was just a small example of how powerful this can get, and how you can utilize the S parameters in AWR Designer. There are a few other places where they can be used, but I think I will cover at least one of them in the future videos. Anyway, thank you very much for watching.